Welcome back to session 8 on unit number 6, dimensional analysis and simulator. This session we are going to discuss the Euler model law. Euler model law in a fluid system where pressure forces alone are controlling forces in addition to the inertia force. The dynamic similarity is obtained by equating the Euler number for both the model and its prototype. This is known as Euler model law, and according to this law, the Euler number of model is equal to the Euler number of prototype. As per the expression of Euler number, it is V upon under root P by rho. So by using this suffix where Vm is the velocity of fluid in the model, Pm is the pressure of fluid in the model, ρm is the density of fluid in the model, and Vp, Pp, and ρp are the corresponding values in the prototype. When ρm is equal to ρp means if the same fluid is used in model as well as prototype, the densities are same. The above equation can be reduced to this. This law is generally applicable for the flow problems where there is a pressure rise or pressure difference occurs, not because of friction, but because of the other things, like because of change in velocity or because of the sudden change in cross sections like that. So there it is applicable. So most of the enclosed fluid system where turbulence is fully developed, that means viscous forces are negligible and the force of gravity and the surface tensions are also entirely absent. In that situation, the Euler model is used. Secondly, cavitation phenomena where there is a sudden rise of pressure occurs because of the collapsing of the bubble. So there also we can use this Euler model. Now we apply this Euler model to one of the numerical. In an aeroplane model of size 1:40 of its prototype, the pressure drop is 7.5 kilonewton per meter square. The model is tested in water. Find the corresponding pressure drop in prototype. Density of air and water is given. Viscosity of air and water is given. So first of all, we'll write. So this is the situation actually. The pressure drop here, as the viscosities are given, means this is the total pressure drop. It takes into account the frictional resistance as well. The total pressure drop that is in case of aeroplane, that is a form pressure drop that is and frictional pressure drop. So form drag plus friction drag. So the pressure at this point, that is the stagnation point, is maximum. Pressure at this point is minimum. So the difference it gives the form pressure drag. Also, there is a drop in pressure occurs because of the flow of fluid when it flows over the skin of the aeroplane. So because viscosity is given, so in association with the Euler model law, the Reynolds model law is also applicable. In most of the cases, it happens because if the frictional losses are given, then we have to take into account the viscosity as well. Because the viscosity difference is also considerable. And that's why we consider that. So as per the given information, the length ratio is given. So obviously this length ratio is LP upon, because the model of the aeroplane is smaller than the prototype. So this is LP upon LM. Pressure drop in the model is given. Then density of the water. Density of water, because in the model case, water is used. Because model is tested in water. So water quantities are related with the model, that like density and viscosity. And air quantities are related with the prototype, like density of air and viscosity of air. Now we have to calculate the pressure drop. So as per the Euler's expression, it is V upon under root P by rho. But the velocity is not given in the example. So first of all, we have to calculate the velocity with the help of Reynolds model. So according to Reynolds model, that is rho VL by mu, that is for model, that is equal to rho VL by mu, that is for the prototype. It can be changed because depending upon the quantities. So sometimes it is VL by nu, or sometimes it is VD by nu if the diameter is given for the pipe. So the Reynolds number may change based on the given information. Now here, density and dynamic viscosities are given. That's why we use this form of Reynolds model. Now in this equation, all quantities are given except Vm by Vp or Vm Vp. So putting all the values, that is densities of model and prototype, viscosity of model and prototype, length ratios. So we get Vm by Vp, that is equal to 2.755. Then according to Euler model law, we have V upon under root P by rho for model, that is equal to V upon under root P by rho for prototype. The same expression can be written in terms of pressure drop. So P can be replaced by pressure drop. So V upon under root delta P by rho. So only unknown in this equation is delta P of prototype, that is actually expected, that we have to calculate. So after putting the values, we can get the pressure drop in prototype, that is 1.225 Newton per meter square. So this is a pressure drop of prototype. So obviously, the pressure drop here is less because the model is tested in water, which is having a higher density as well as higher viscosity. So because of higher density, more drag force it can experience. So that's why in case of prototype, the values are less, 1.25. So that's it from this session. At the end of this session, you could be able to explain this Euler model law with its specific application, and you'll be able to uh, apply this Euler model law for solving problems. Maybe through practice, you can apply this particular law in real world application as well. This end this session. Thank you very much.